my starter question, if you guys want to put in the chat box, what is your favorite mode of transportation? Is it an airplane, car, boat, bicycle, foot, skiing? That's pretty cool.
Running.
I would probably say mine is airplane or a bicycle. I love airplanes just because I love the way the world looks from up there. It's all very neat and it looks quite manageable. Yeah, of course, that always changes the moment you land. Yeah, if you guys could put in the chat box, what's your favorite mode of transportation? Train. I like trains too. When I was a kid, 5th through 10th grade, I lived in Japan, and you could get literally anywhere by train. It was fantastic. At the age of 10 years old, I could go into one of the world's biggest cities by myself quite easily because the train allowed me to, and because it was an incredibly safe country. The freedom I had at that age was amazing. When I came back to the United States and we moved into a suburban home, I felt trapped. And that was when I developed my love of bicycles, because I wasn't old enough to drive yet. So I got on that bicycle and I took that bicycle everywhere. All right, well, we're past half now, so I will get, in terms of people who need to show up, we'll get started. Today is about trusses, and the reason I asked what's your favorite mode of transportation is that most forms of transportation end up using a truss somehow. If you're on a car, you always end up driving over some bridge that's a truss. Airplanes have a lot of trusses in them. Trains, I don't know. I have to think about that, but you bump into a lot of trusses when you're traveling. They are incredibly strong for their weight and are quite useful, so they're fairly common. Let me share my screen. We'll go through the canvas here. Is that right? Hold on. I'll be back in a second. There we go. So what are we doing in this lab? We're doing two things. Primarily, most of the lab is spent on looking at zero force members in trusses, learning how to determine where the zero force truss members are in a truss. We do this primarily because it simplifies the problem. If you can identify zero force truss members, solving your problem will be significantly easier. The number of evaluations you'll have to do an analysis is reduced greatly. And people say, well, often, why would you design a truss with a zero force truss member in it? You probably wouldn't, but the deal is that the load varies from time to time, depending on what you're doing with that truss at the moment. So at some instances, when you're evaluating a load, there may be truss members that don't have any forces in them, and another times that same member may have a load in it. But depending on your analysis, you want to look for all those zero force truss members and eliminate them. The second piece is I'll spend a brief time showing how to do the method of sections. I'm not going to spend any time on the other method for solving trusses, which is the joint by joint method. That is fairly straightforward, I believe. It is a bit tedious, but it is straightforward. Basically, it just means that you take at each of the truss intersections, you do a equilibrium equation and solve for it, and you just sort of work your way from left to right or up or down. Pretty straightforward. So looking at this, I just put this up here because there's all kinds of trusses and different ways to design trusses. And I don't know how these people got their names associated with the truss. Both perhaps they were the first one to do that. The ones that I'm most familiar with would be the Warren or the Howard Pratt, which are very similar, just kind of different directions there. And those three are often seen in airplane structures. And that's why I'm most familiar with them. I'm a member of the Experimental Aircraft Association, and the idea of building a plane, it appeals to me. The time constraints of building a plane has yet to happen. But always been interested in building a plane. And that explains why this next little bit is here. I just wanted to show you all the different trusses. In the old days, when they were fabric covered airplanes, trusses were the main way to build a light and strong structure. And if you look at the frame of this small aerobatic airplane, I don't know if it's a Pitts, or I can't remember what it is, but you can see it in the green, the frame there. Also, all of the ribs of the wings that make up the airfoil are all trusses. So it really is one huge truss. And it's shown a little bit more on the right there. That's the probably the frame of the plane, the body, the fuselage. So, and this one's a Warren truss. Of course, planes have changed a lot. A lot of times now they have frames that are sort of like trusses that go across, and then they have a skin along the outside, and this is called semi-monocoque. That skin now is what they call stressed skin design. It means that the skin is carrying some of the load. In this fabric-covered airplane, the fabric does not carry any of the load, at least structurally. It does carry the load of the plane, but it creates the lifting force, but it doesn't the structural members. And then we have the complete monocoque, which is, there's no trusses in there at all. All right, I'm sure Joanne did this, but we're going to go over this just so that you get this nailed. The assumptions of trusses and some of the rules. The first one is that all loads are applied at the joints. Thus, the weight of the truss member itself is neglected. If you use the weight of the truss member, then you would have another load somewhere in the middle of the member, not at the joints. This, in essence, makes it a two-force member. If you recall from our last lab where we had the scissors jack, we had several two-force members in there, and you can remember how that sort of makes things easier. You no longer have to worry about moments somewhere else, and also it makes things easier. I'm not going to blabber on there. The other thing that I want to point out about that, and we talked a little bit about this last time, is that this isn't an unreasonable assumption. Generally, the weight of the member compared to the loads that it's carrying is significantly larger. That is, the loads are so much larger than the weight of the member that you can pretty much ignore it. It's usually 1/100th of the load. It's amazing to me. That's the great thing about trusses, is that they carry a huge load for the weight that's involved to make it. And the second assumption is that the members are always joined together by smooth pins. And if you recall from the reactions, that support smooth pins means that there's no moments translated at the ends. Again, that's sort of those two things sort of define what a two-force member is. So the assumption really is that all trusses are made up of two-force members. So let's talk about zero force members in a truss. This is one of the first things you do when you're analyzing a truss, is you just look through it to see if there's any two-force or any zero-force members in there. So first thing you want to do. So there's two basic rules. Some people have kind of added some other rules I've seen. I've got a video attached here somewhere. The guy discusses the third rule, but really what it is it's sort of he's just taking the same rule and applying it twice in a row, basically. You could have gotten there by just applying these two rules. So these two rules are really the essence of what you want to do. The first one says that if a joint is non-collinear, and that means not in a line, but at some angle, other than 180 degrees or 0, depending on how you look at that. And there's no load on it. There won't be any load in either one of those members. So if we look at this diagram here that I've got, we've got, let's look at this one down here where they circled the joint A. You can see that there's no load at A, so there'll be no force in this member AF or in AB. And the same can be true up there in at joint D. We've got E, D, and DC. Both of those members become zero force members. Again, that's because these two members are non-collinear and there's no load applied at A or at D. If we go on to the next rule, and I'll do some quick examples in a second here. We have the rule that basically states that if you have three members, two of which are collinear, i.e. two are in a line, and then the third one intersects it at some other angle, then the third member, which is not the collinear member, is 0. So if we look at this, we look at D, and we have E, D, and C, which are collinear, so we've got a line there. And then we got this other member, AD, intersecting at D. So the the zero force member would be AD. And the same can be said of C here, where again, D and C and BC are collinear along there. And then there's this third member coming in. And so therefore, member AC would be 0. So that is the two basic rules that you need to apply. We'll do some examples, but first I wanted to show you, if we go here, zero force members, simplified structures. Why do we do this? If you look at the top, that is where the whole the whole truss is in place. And then the next step is we've evaluated for zero force truss members, and we can basically ignore those. And then the force, or I should say the truss, takes on the look of the truss below. All right, I'm going to stop sharing my screen for a second here. I'm going to switch videos. Oh, in regards to was I an Army brat? The answer is no. My father was an engineer, and he got a lot of different jobs, and we moved around a lot. That was back in the day when people would move to move up in the chain of command. All right, I wanted to show over here, and let's see. So this is my baby truss. So if I load, and imagine my fingers are loads, so my right hand, the lower hand, is the supports. If I'm supporting here in the middle and then off to your left side, and then I've got a load coming down at the top, that first rule we discussed, you kind of see this thing rattling around a little bit. The right side, this one and this one, those two members are zero force members. So that's an example of a zero force member based on rule 1. So these two would not have any forces in them. So they're zero force members based on this loading. And this is why I said it changes. So here I've got basically the same truss right here. And now I've got the supports at the ends where my right hand, which is this one. And I've got that support. Oops. I did this without falling apart. If I'm pushing down like this, so I've got the load at the top where my left hand is pushing down, and then I've got the reaction that's the supports where my right hand is. Now this is one, and the reason I created this little truss was this is the one that somehow throws students off all the time. I am putting a load directly down on top, and everybody says, gosh, that middle member has to have a load on it because the load is applied right at the top, right on top of it. Why isn't there a load in there? Well, there isn't, because if you look at the bottom joint in the middle, If you did a equilibrium equation, if you did the sum of the forces in the y, you would find that there is no way to balance the force if there was one in the middle, on the middle member. And in fact, I can actually like flick this thing off. You can see how loose it is. It just falls off, and nothing happens there. And so that force has that member has no forces on it. Now, if I relax things, it falls all apart. So it's clear that these two members at the bottom are in tension, but they're equal and opposite to each other, and there's just no way to balance this force in the middle. I really wanted to show that because, like I said, I have a lot of students argue with me vehemently that there must be a force in that member, and I can tell you that that rule, the second rule, applies if you do the equilibrium equations. So are there any questions about this? I hope this is clear. This is the basis of what we're doing today for the most part. I'm going to go on to the method of sections if there aren't any questions. All right, no worries. Like I said, the rules read simple. Sometimes in practice, things get a little lost. So let me share my screen again. So here we are. We've just looked at zero force members. The one here in the left is from rule 2, where we have the collinear and an intersecting one. So that's why that one disappears. And this middle one is the first rule, where there's two non-collinear members meeting and there's no force on the middle of them, and therefore these disappear. So these disappear down there. You can see it. And again, this is rule 1 over here. All right, let's talk about the method of sections. The method of sections is a really powerful way to solve trusses, particularly if you're not interested in knowing every single force in the truss. You know, the way that you might consider doing a problem if you wanted to know every single force in every member might be the method of joints by working your way across, because you have to solve for every single joint anyway. So that's a fairly straightforward way. You just kind of walk your way across. But the method of sections allows you to take a truss diagram, as you can see on the left here, and then there's this little dotted line, and then just cut it. And you can cut it. You can cut it anywhere. It does not matter. But what you end up with is some free body diagrams. So instead of this one large free body diagram, we now have 2 free body diagrams. The great thing about trusses is we made that assumption that everything is a 2-force member. So you can see that we can draw the forces along the lines of the truss. We know that the force in those members is going to act along those lines, and so we know the orientation of the forces. So we can draw E and BE and BC, those forces, and we can do the same on the other side. So now we can analyze that, those free body diagrams, either the right side or the left side, as we choose. The one thing I want to point out in this method is that when you do moments, you can take a moment anywhere. Everybody assumes that it has to be on the body. For instance, a lot of people would take, for instance, a moment at B, if they were looking at the left side, or at F, or at R1 here. But you could take a moment at E, which is not on that left-hand free body diagram. But you can do that, because anywhere relative to this free body diagram, anywhere in space, the moments should equal 0. So you can actually take moments off of the diagram. And the reason you would do it at E is because, well, the force E and the force BE intersect there, and of course you would cancel out some of your moments. But that is just something I want to point out. That's a very powerful tool that I see a lot of students miss and forget when they're trying to solve exam problems.
Rob?
Yeah.
Question, does the method of sections require a straight line cut?
No. I mean, you can see they've kind of done this wiggly thing.
Wow.
It does need to be cut free. It doesn't really matter because, again, because of the 2-force member assumption, we know what line those forces are acting on. We know that they're going to be acting along the same, the same line as the truss member itself. So it doesn't really matter. All righty. So I wanted to do a couple of problems. And this is the first one. You can kind of follow along. I'm going to stop sharing my screen and go back to my board. So can you guys see that? All right. So anybody have any ideas about which members on this would be zero and under what rule? Anybody got any guesses?
Rule 2.
What's that?
Rule 2.
Yeah, rule 2 is going to apply here.
Okay, and would it be B to G? Because it would be A to B and B to C would be collinear. And the third one would be B to G, which is not collinear, correct?
You're talking here?
Yeah.
And then here?
Yeah.
All right. So maybe it's not clear. This is a force being applied right at this joint. And here's another force at this joint. So what we have, and maybe I wasn't clear on the rule, I think that's the problem here, is that we do indeed have this collinear member right here. As we said, A, B, and B, C, those are in line. And we do have this third force coming in here, third member coming here, but we have a force acting on there. So if we were to take the sum of the moments, or sum of the forces there, if we were to do the sum of the forces at B in the Y direction, we would have, the force, and then that would be minus. And then, the other thing that we assume in all trusses is that things are in tension. So again, I would draw this as a minus, because my joint here at B is going to look like this. It's going to have F, and then I'm going to have AB, BC, and then BG. So in order for this to be 0, there has to be no component of F that is in the direction of BG. And that is not true. So we would actually end up having something there. So the sum of the moments in the vertical would be BG times cosine of some angle. I don't know what the angle is, but there would be some angle in there that we would need to figure out right there. And so this one does not qualify. But if we look at the other side over here at D, we don't have a force applied. So if there's a force applied at this point, the rule doesn't apply. It has to have no force applied at that joint. So over here, because of this, if we did, like I said, this is not going to be equal to 0 because there's going to be some balance. But if we look here at D, we do the same thing. We had a forces. We'd have DE and CD, and then we would have DF. Now, CD and DE, because they're equal and they're in the opposite directions, they have to be equal to each other. And that leaves nothing for DF to be balanced going this way. So DF equals 0. So that is our 0 force member right there. Our next one if you get stuck and you're not sure what what's happening, just do your free body diagram at the joint that's in question. And hopefully the answer will come out clear. I said that's a lot of the source of the arguments is that nobody has done the free body diagram and worked it out. So, all right, let's apply a force here and a force here. 2, F1. So here, anybody want to gander what would be 0 here? Do we have any 0 force members?
We have a 0 force member from BG and DF, I want to say.
Right. So when you're doing the problems, if you could circle or put an X through the member you think is it, and then come over here and go BG, DF. That's how I want to see the problem solved. Just put an X to the ones you think are 0 and then label them over here, just in case there's any confusion. That way, if you're scribbling a whole bunch of times, this becomes the answer. So yes, this is it. This doesn't qualify because it's got 4 joints. This here doesn't qualify because even though that's 0, and we now have really only one member there, we would have the collinear here, and we'd have the third member coming down. The reason it doesn't is because we've got a force applied at that joint, and the same happens here. All right, let's do the next 2. So that first truss was a Warren truss. And I can't remember, this is either a Pratt or a Howe, I can't remember which, but it's one of those 2. And we've got our truss again. And the reason I'm drawing a pin and a roller is to make sure that this problem would always be statically determinate, i.e. we'd be able to solve it. If this was another pin, the reactions at the support, we would have 4 unknowns in a 2D problem, and well, we couldn't solve it. So that's why I always draw the roller. We have a force coming down here, and a force here, and of course I got rid of my labels. A, B, C, D, E, F, G, and H. All right, what about here?
Point H, so then BH is the 0.
Right. So this is our collinear member right here, and then this is our intersecting member. And because there's no load at H, BH becomes 0. All right. We see something else that's similar over here. We've got, again, collinear here, but we have a load here, right? So this one, that one doesn't qualify. So I don't think there's anything else here. If, let's just say that this wasn't there. So now this one would qualify. And what I want to talk about, the reason I'm doing this is to talk about what happens when what I call cascading. So once I've got this one 0, I essentially have collinear members here, and I've got a third member here because this one no longer exists, really. It's a 0 force member. So this one also becomes 0. So in this case, it would be DF, and DG.
Hey, Rob.
Yeah.
Sorry, I don't get how the BH is 0 because don't we have the force acting right on the joint? I mean, I get it from the bottom, how there's collinear and there's not a force acting right at that joint.
This is the same thing that we just talked about right here. Was this thing. When I'm pushing down, everybody says, well, there's got to be a force in there. There's got to be a force in there. But
Yeah.
there can't be a force in there because if you were to put a force there, let's evaluate at H. We did H. And we draw forces HG. Notice I'm always drawing them in tension. And AH. And then I said, well, there's got to be a force in there. Let's put it in there. BH. Now, when I do the sum of the forces in the vertical, of course, I can do the sum of the forces in the X. And we get AH minus HG. And so therefore, we find that AH equals HG. But what about here? If we do the sum of forces in the Y, we get 0 equals BH, and then there's nothing. So what becomes clear is that BH is 0.
Okay, so that force at B is distributed down AB and BG and not BH.
And there might even be some tension in C.
Right, yeah.
So until we solve it, we don't know. But we do know that we can't have a vertical force at H. So therefore, BH is 0. And that's what rule number 2 is all about.
Right. Okay. Thank you.
No, that's a good question. And I struggle with that one, getting students to see it all the time, because this is exactly the situation where people think there's got to be a force in there. And if you just follow the rule or you do a free body analysis at that joint, it quickly becomes obvious that it's not possible. All right. And the next problem was to put the load here. And since I already removed the load here, basically the same thing happens. We now have this, and this. So again, same reason for this one here. The load didn't change on this side. BH is 0. We start here with collinear members here, and then member DF being 0. And then that makes member GD also 0. This is the cascade effect. And when you're doing these problems that are coming, make sure you go back and reevaluate after you've eliminated what I call the low-hanging fruit in terms of what's a 0 force member. All right, we spend a little bit of time on the method of sections, just a little bit. And we'll go back to so if you look at that, that describes how to go about solving a method of sections problem.
Rob, I have kind of a theory question.
Yeah.
The only reason this method of sections works is because it's a truss, right? Is because of the way it's all 2 force members. You can't do that with other statics problems, right?
In the essence, the answer is yes. It still could be done, but not easily. Let me elaborate on that just a little bit. But you're basically saying the correct thing there, David.
Okay, thanks.
So here's our truss. And They put a load right here. And of course, we'll have reactions at each support. So the method of sections, as David was pointing out, the whole reason this works is because we know that the forces are in line with this member. So that when we make this cut, we know that the forces will be like that. So when we draw the free body diagram, and let's say we draw the free body diagram on the left side, and I've done that for you and I've done my lovely little chop. So now I've got a load and reaction. And in order to balance this side out, I'm going to draw this, this, and this. So that would work. If this was a solid body, this is what David's question is, if this was a solid body, would that work? The problem is that you won't know the direction of the forces, or really even where the vector is, where it's emanating from. So if you knew that, you could solve it. I mean, the concept of a free body diagram always works. It's just that it will become what is called indeterminate. You won't know enough information to solve the problem. This is still solvable, and we could do several things. We could take, to solve this, usually what they do in the method of sections is they have you solve for the two reactions first, just like we did in the lab we did the reactions where we had the chair and the bicycle and the pencil, is you could solve knowing these distances and this force, you could figure out what these two reactions were. And so then this would be a known, this would be a known. So your three unknowns would be this. And the easiest way to do this would be to take either a moment right here, because we would get rid of this force, and this force, because they are concurrent at this point. All three of these forces are concurrent at this joint. So the only two forces in your moment equation would be these two, right there. You could also take a moment right here. Even though it's not on your body, you can still take a moment there. You don't have to be on the body to take a moment. And you would do that again because these two forces are concurrent right there. So you know that this force and this force do not contribute to a moment where these two forces intersect. So then you would have this, this, and this. So in essence, if you took a moment here, you could solve for this force. If you took a moment here, you could solve for this force. And then at that point, it's just a matter of doing the sum of the forces in the vertical and the sum of the forces in the horizontal, and you could solve for this one. So that would be fairly straightforward. And that's what they described there in that plot there. Let me go back to showing my video because I think some of what I was talking about was gone there. So when I do this section, I know that the forces act in this line. And so when I draw the free body diagram of the left side, I've got my section, I put my forces on there. Again, I draw them in tension, and I know they act along this line. And I was saying that initially what you often do in the method of sections is you solve for the reactions first, here and here. So we would solve for, R1 and R2, and we would know W, the load. And so by knowing that, R1 and W, when we go to solve for these forces in these members, we could start off by taking a moment here, because these two forces here and this force, they're all concurrent, and we would take the sum of the moments at that spot. And the only thing that's left in our equation would be this force R1, which we know, and this force up here, which we don't, but we know the distance. And so we could solve for this force. And then just again to describe the other place to take a moment would be here, where the two forces intersect. And again, that's not on my body, but it's where the two forces intersect. They would be concurrent at this point. So these two forces would not contribute to a moment. So then the only things left in my moment would be this force, and this force. And this is the only unknown, and we could solve for it. And then after that, it's just a matter of summing either in the horizontal or the vertical to solve for this last force. I'm starting to get long-winded here, and that usually means people falling asleep. If you look at the remainder of that page on the Canvas page, there is a video there. The guy described it, the same things that I just did. He probably does it more succinctly, but it will be different, and it might help you. Also, if you look at that page, let me share my screen one more time. I did several more examples, and I called out what rule was each one. If you look at this first one, you can see that basically it's what we just did was the one that we did at the top. I think it's the same problems. Yeah. The bottom ones here are different. The one that I want you to look at is the very lowest one here. And actually, there's no load on that. I should have put a load on there somewhere, but there are no zero force truss members. And the reason is that neither rule 1 or 2 applies anywhere on this. You might think that it would be at DF because GF and EF, but those GF and FE are not collinear. So there's no zero force truss members in this truss anywhere. All right, on to the assignment. So there are 18 trusses for you to look at. And I want you to find the zero force truss members in all 18. To give you some idea, because I'm well versed at this takes me about 20 minutes to do. I can whip through these things. It's sort of like easy crossword puzzles for me. I expect it'll probably take you a little longer, but I can't imagine too much longer. If you follow those same rules and work through it, it should be pretty quick. There are 2 files to download. You can download those files and work right on those files. You can just circle the trusses that you think are 0 and label, or I should say, list the force in the members that have 0 force right next to it. So just go in there and circle and then list to the right. You can either use the PDF or the Word doc. I want to point out one truss that usually causes people to have questions. We go down to here, truss number 17. If we look at truss number 17, what a lot of people think is happening is that there's a connection there between EE and CA. This point where there is no dot, there is no connection. So there is no connection there. There is no pin. They are passing each other. So, and it's the same over here in the other joint. So that's about the only thing on that I really want to point out. There is one method of sections problem I want you to do. You can see that I'm asking for the forces in 3 members, which is BC, BE, and DE. So those 3. So it makes obvious sense that if you want to solve for the force in those members and you don't really care about all the other forces in the rest of the truss, is to draw your section right through there, right through DE, BC, or BE and BC. The other thing I wanted to point out, and it's in the hint there, is that you don't need to solve for the reactions on the wall. Just use the free body on the left-hand side to solve for the problem, and it should count. All right. So if you have any questions, now is good. I'm going to send you into the breakout rooms. There is an extra credit there at the bottom. It's a question, so half a point. All right, let's start some breakout rooms. All righty, here we go. Hey, Isaac.
Hey, Rob. I was wondering if I could go into room 5.
Yeah.
Thanks.
I can put you there.
Hello.
Hey, Matthew.
Hey, oh, you're still recording, by the way.
Oh, yeah. I'll stop that.